Hello, good morning, and always good afternoon to our colleague in Europe, from Poland, from Italy, from France, from UK, and a good evening to our friend in Asia, Beijing, Tokyo, and Singapore. So welcome you again to this World Large River and the Delta System Source to Sink webinar series. And today we invite Philip Minderhoud to give us a talk about the Delta subsidence. So before I introduce Philip, as always, I want to say this coming Friday on October 30th, Professor Robert Eller from Stony Brook University, he will talk about tropical delta, particularly focused on the carbon processing, mineralization, and weathering process. So same time, please do remember only this week in Europe, because it's 1 week earlier and the daylight saving time. So it's London will be 1 p.m., Paris will 2 p.m., still US East Coast still 9 a.m. and then Beijing is 9 p.m. So also next week, we have 2 more interesting talks. Pete Tolling from Durham, University of Durham, he will talk about turbidity current and sediment transport through the canyon system. And also Dave DeMaster, he will talk about radiochemistry and how the sedimentary process in major delta system by studying the latitude 10, the carbon 14. He will talk about his past study Amazon, the Yangtze, and the Mekong system, and also Antarctic. So please come back also next week. And Philip, as you can see here, Philip received his PhD and with the topic of sinking mega delta, and particularly focused on the Mekong Delta. And then after that, he stayed in Utrecht University for 1 year postdoc, continue work on the future Delta Research Hub. And then 3 months ago, he came to Italy with a fellowship, the EU Marina Curie Research Fellow at Padova University. And this university is very famous, is set up in the 2021, 800 years ago, one of the oldest university in the world, and it's only half hour to Venus. This is no wondering why they have that kind of fellowship support him to study subsidence in the delta system. We know the Venus and the Pearl River delta nearby. So I think I will give the floor to Philip. Philip, now you can share your screen and put a presentation mode.
Okay, I'm sharing my screen. Thanks so much for the introduction, Paul, and also for the invitation to this lecture series, which I'm looking forward to bring a bit of contribution to. So hello, everyone. I'm going to talk in this talk about sinking sinks, and the reason I name it like this is as we are in the Source to Sink lecture series. And I will talk about subsidence in deltas. And these deltas are at the end of these source to sink systems. And this is where, let's say, in normal conditions, the sediment that comes down through the source to sink system is partly being deposited. And I will talk about causes and also the consequences of land subsidence in these deltas. So before we start, I was hoping to be able to fill this page with beautiful pictures from actually an experiment in the Venice Lagoon that we are currently doing. But I had some issues with the internet of uploading the pictures. So unfortunately, I cannot show them on this slide, but I do want to, let's say, give you a bit of background. So we are now, as we speak, doing a compression test inside the Venice Lagoon. So instead of what you would normally do if you want to know some characteristics of the subsurfaces, you would take a sample and you bring it to the lab. Well, we actually did the other way around. We brought the lab into the field, into the lagoon. You can see some examples on, for example, Twitter and LinkedIn coming up in the coming days. So this is a teaser, and I hope you can look at what we're doing right now on these other platforms later. So let's start from a global perspective. So here we see planet Earth, and this would be if it would be night all around the globe at the same time. This is what you would see from space. So you can actually learn quite a lot from this rather beautiful image. Well, for most, we can see we are with many, right? There's lights being produced everywhere, and it's really a sign of humans living there and doing all sorts of activities. And the second thing is that we really like to live along the coast, because many of the continents and coastlines are very clearly illuminated. Well, and this has, of course, a lot of reasons. It's often very pleasant to live close to the coast. So one of these places where a lot of humans have settled in the past and are still increasingly settling are river deltas. And here we see a couple of large river deltas on the planet. And in color, you see the elevation of these deltas. And the more warmer the color, so the more red, means the lower elevated these areas of land are. And this is directly also the conflict in these delta systems, because they are very low lying and close to sea level, or even sometimes almost below sea level. They have a high exposure to challenges like sea level rise and all sorts of pressures. Well, these deltas are very valuable areas. They are densely populated. We have more than half a billion people living in these areas. They have a lot of resources, very fertile land, and they are producing a lot of food that we use daily to fill our stomachs. So let's have a look at the changes that have happened in these delta systems around the world. So here we see a schematic cross-section of a delta in a natural state, so before humans started to occupy these areas. Then we moved in and we started to settle, and we started to change the land use. For example, to create agricultural practices for cropping. We also built big cities, and these cities are increasingly growing these days. And we started to exploit the natural resources, for example, groundwater. Then we also changed a lot of the upstream domain of these deltas. And there's a lot of the previous talks in this lecture that have addressed, for example, the impacts of upstream damming on the delivery of water and sediment to these deltas. And in the delta itself, we are very keen on using the sand from the rivers, because it's really excellent material for building all our big cities that we're growing. So all these changes are actually on top of the changing climate. So this causes quite some processes that are, let's say, affecting our daily lives in these deltas. For example, flooding, we see an increase of that. We see an increase of salinization happening in the estuary system. We see more and more coastal floodings, the erosion of coastal areas, the intrusion of salt water in the subsurface. And for example, if we extract too much groundwater, we also cause additional mixing and upconing of more salt water. And as you all know, we have these days rising sea levels. So sea level rises, depending where you are, on average about 3 millimeters per year. And these deltas themselves, they also are not stable landforms, but they experience land subsidence. And these land subsidence rates can be quite high, as you will also see throughout this talk. Well, if you add these two together, then you arrive at what we call relative sea level rise. And this is what you experience when you're standing at the coastline and you watch the water level going up or maybe down in some cases, but in these deltas mostly going up. So that's the relative sea level rise. So with all these changes that are happening, our river deltas, because of their low elevation, are the first ones actually that are feeling all the issues of these environmental changes, and they are the first one to go down. So you can actually view them as the canaries in the coal mine. These are, if you want to put it like this, this is, let's say, the front line of our battle against relative sea level rise. And in the past, let's say in a natural delta system, sedimentation is the coping mechanism of these deltas for relative sea level rise. They are built out of new sediments delivered from the upstream domain. And this is also the mechanism that naturally maintained them and was able to follow sea level rise in the past. Well, if we look to the right diagram, we actually see an assessment of major delta systems around the world. And all the delta systems that fall below this red line, it means that there's not enough sediment available in the entire river systems to elevate the delta plane to actually 1 meter sea level rise by the end of the century. So we see here that a lot of these deltas are not receiving enough sediment already. And well, as I said before, there's other talks in this seminar series that are going into detail much more on this. So before we go into depth on land subsidence, I want to give you a small, let's say, background on the difference between subsidence, sedimentation, and elevation change. So let's start with some definitions so we all know that we talk about the same thing. So land subsidence is the downward motion of the level of the land, and it is the negative vertical land motion going down. So vertical land motion, which can either be subsidence going down or uplift, plus global sea level rise is what we call relative sea level rise. And then vertical land motion plus sediment accretion or erosion is what is eventually causing surface elevation change. And we see that here in this diagram. So what is called here MH is the marker horizon, and this is actually a diagram to what we call a relative surface elevation table measurement method to let's say measure elevation change and land subsidence. But what is important in this graph is that subsidence and sea level rise are both measured according to a certain level, and this level is not equal to necessarily your surface level throughout time. And this is because sedimentation is not included in this horizon, which can actually go down when it is sinking. So this means that sedimentation is not affecting relative sea level rise. And there's been a bit of confusion about this in the past also because sedimentation was actually included in the relative sea level rise equation of the 2009 Savitsky paper. But strictly speaking, if we look at the definitions, this is not something which is part of relative sea level rise. This also means that sediment starvation is not a cause of delta subsidence. In fact, the other way around, sediment incretion actually increases land subsidence rates. And we'll go into detail a bit later, but this is because they add loading to the subsurface because of the weight of the new sediments. So what it does do, so sediment starvation is causing elevation loss. If you have less sediments, it means that the mechanism to counterbalance land subsidence and sea level rise is reduced. So this is how, let's say, land subsidence connects to sedimentation and to elevation change. So let's have a look at delta subsidence. So in this diagram, I will show you what kind of processes and drivers can cause land subsidence in a delta. So we see a cross-section of a delta subsurface. And as said before, first of all, land subsidence is a natural process. It can happen due to the loading of natural materials. This can be new sediment, this can be water, this can be biomass, and they cause a loading effect, which causes consolidation. Also, the more sedimentation you have, the more loading you will have, and the higher the rates of land subsidence. So this is a bit maybe counterintuitive, but this is how it works. Then we also have natural processes that are stemming from the deep subsurface. So this can be isostasy movements, this can be tectonic movements, and they can also cause, let's say, vertical land motion at the surface. Then land subsidence can be accelerated by human activities. For example, by the addition of loading at the surface, simply by adding new and heavy materials, but also by increasing the load because of draining surface water. So when you lower the groundwater table at the surface, you actually also increase the effective stress, the load, because the water no longer supports the grains. So that means that you also add weight to the entire system. And I have to say, another process that you will cause is that you also cause oxidation process. So any organic material in the subsurface will start to oxidize and will also lose volume therefore. Another process that will cause consolidation is the extraction of fluids. This can be groundwater, this can be hydrocarbons. And actually all these processes together, they form the entire system, the entire signal of land subsidence. So they can stem from different depth domains, shallow, medium, or deep, or however you want to quantify them. And if you add them all up together, you get to this total signal of subsidence. So there's basically two ways how you can, let's say, tackle land subsidence. You can either start with a measurement of total subsidence right here, and then your challenge is to go into the depth and try to unravel which part of your total subsidence is belonging to which part of the depth-dependent subsidence. And then when you know that, you can start to work your way towards what processes are actually causing this subsidence at the different depths. There's also another way. You can also turn it around. So you can also start at the process itself, for example, the drainage. And through physical models or calculations, you can compute the effect in the subsurface and then arrive to the contribution to the total land subsidence. So these are two ways how you can, as a researcher, let's say, try to tackle land subsidence in a delta. We can also split these different drivers in some groups if you want. So for example, the ones on the left are usually causing shallow land subsidence and also local effects. The most easy one, for example, a building will cause land subsidence for the building itself and maybe its direct surroundings, but it will not cause your entire delta to lose elevation. Well, on the other side, if you have these deeper rooted causes, they can actually cause more regional signals of land subsidence. Okay, if we compare human-induced processes to natural-induced processes, we see that human-induced processes, they tend to be much faster in rates than natural processes. And it's also the case that land subsidence can be highly variable in time and space. So this makes, let's say, this puzzle that we see in this diagram quite challenging to solve, because the puzzle will change also from day to day and from year to year. So let's have a look at, for example, the spatial component of land subsidence in a delta. So we did an analysis for the Mekong Delta in which we compared subsidence derived, inside-derived subsidence rates on the left, and we compared that to land subsidence maps and a time series of these on the right side here. Well, what we see in this diagram is a link between different land use types and the mean elevation, the mean subsidence rate that they are experiencing. And what you see here, these are drivers that we saw in the previous diagram of human-induced land subsidence. So there, for example, the drop in surface water, groundwater extraction, and the loading of buildings. And we try to classify the impact of these drivers for each of these land use classes. And as you actually see, going from lower subsidence rates to higher subsidence rates, we also see an increase in expected effects of these human-induced drivers. I will also help you a bit with the land use classes. So, for example, these are natural land use classes, so hardly or actually no impact of human activities, so marshland and wetland forest. These classes are agricultural classes. So there's already been a land use change in the past from a natural class to an agricultural class, and there's been ongoing human activity in these areas. And then on the far right side, with the highest rates, we see the urban areas, and they also tend to score. They score highest on all the drivers of land subsidence. So we also have this one. This is the mangroves, which show quite high compaction rates, but this is because they're actually situated along the coast. You can see it here. It's this green group, and these are actually locations where the natural compaction rates are really high, and we'll come to that also later on a couple of slides. So what we see is that there's higher land subsidence rates when there's an increase in human-intensive land use. So humans really drive land subsidence in this case. And we also looked at the temporal component. So can we see, if we compare the land use change over time, also a change in rate when we see changes in land use? This diagram is a bit hard to grasp, maybe for the short time that we're going to look at it. But what it shows is that land uses that do not change, they have typical land subsidence rates, which are visible in this column. Then land uses that do change in the period from 88 to 96, from land use class 1 to land use class 2, they have actually rates which are closer to the new class. So you see that we see here the change which is relatively recent, and this is the change which happened already 2 decades before. And we see that land use that changed earlier on has rates which are closer to the unchanged land use. So that means that shortly after a land use change, the rates are not that much different from the previous land use. And this is because land subsidence, it's not a fast process, but when the system changes, it also slowly changes the amount of land subsidence that is caused by this environmental change. So we see the temporal signal in this analysis actually becoming visible. And I would invite you to read the paper on this if you want to understand it, let's say, in all details. So another example is the effect of the evolution of a delta and natural compaction. So we see here the evolution of the Mekong Delta, and these are the roughly, let's say, the coastlines at several years in the past. So this is about 3,000 years, 2,000 years, 1,000 years. And this delta really prograded very fast. It's one of the biggest deltas that we have on the planet, and it really grew very rapidly because there was a lot of new sediment being brought up into this system, and there was a relatively shallow substrate on which it could form. So if we, for example, look at the cross section on A to A prime, then we would see this. We see this Holocene deposits of about 20 meters sitting on top of these older Pleistocene deposits. And it really rapidly prograded. So we have a progradation of about 150 kilometers in only 3,000 years. And it is true that if you have very young sediments, that they're very prone to high rates of natural compaction. And there's some measurements being done, for example, in which rates are measured up to almost 5 centimeters a year. And this sounds very, very high for natural compaction rates. And this is actually what we wanted to evaluate, whether this is indeed natural compaction or is there something else going on. So in order to study this, we actually try to simulate this process of delta progradation using a new simulator that's being built here in the University of Padua. And by using this simulator, we could actually reconstruct, let's say, or follow the evolution of this Holocene delta. And we see here in the colors is the amount of overpressure that is present in the fine-grained deposits. And because this overpressure is actually captured and very slowly released, it creates this what we call delayed dissipation of overpressure, and it's causing, let's say, delayed lens subsidence rates. And this delay can be very, very long. This can be in the order of hundreds of years. So it means that even if you don't touch a system, it can still experience lens subsidence rates because of what happened in the past. And for example, the old shorelines, they used to be at the surface and they are now buried several meters below ground because of natural compaction and the additional weight of new sediments on top. And with this exercise, we actually found that you can indeed have quite high natural compaction rates in the order of several centimeters, just as a result of delta evolution. So that means a couple of things. Also, for example, if this is the case for a part in a delta, you cannot stop this process because it is inherited from the past and it's present in the subsurface right now. So the only way you can do is actually you can only adapt to it. And one of the options is, for example, to maintain sedimentation so it can counterbalance this natural compaction. So currently we are actually continuing the development of this simulator. Also in a 3D domain and to include the computation of creep. So it should be really, let's say, cool tool in the future, with we can try to simulate delta systems or prograding systems, or actually any type of coastal deltaic system which has compaction and sedimentation in it. So stay tuned for this development. So another example is the extraction of groundwater. So this is more coming from the deep subsurface. So in the Mekong Delta, there's a lot of agricultural practice going on. There's rice production, there's vegetable production, there's fruit farms on elevated islands, fish farms, shrimp farms. And if we look to the amount of groundwater extraction in time, we see this massive increase in extracted volume, actually since the start of this millennium. So we know that this can actually trigger lens subsidence. So what we tried is then, knowing this extraction rates and also knowing that it comes from the subsurface, which is typically, it looks like this. This is a cross section. And it can be up to several hundreds of meters in depth. And this is quite typical for many large delta systems, that it consists of more sandy parts and more clayey parts, the more fine-grained parts. And what we see is a very steep drop in hydraulic head. So this is water pressure in the confined aquifers, while the phreatic aquifer, which is at the top, is actually not experiencing any drop in groundwater pressure. So a bit of background, what will happen? If you reduce the amount of pressure in the sands, so the aquifers, not much happens because there's a little bit of elastic deformation, but the sand sand grains are quite incompressible. However, if you then go to the aquithards, which are the more clay-like deposits, they tend to have a much looser structure, and they rearrange when there's an increase in pressure. And you can actually, let's say, try to understand this process more easily in this way. If you look to your dishes in the sink, this is the natural sedimentation of dishes, right? And there's also a lot of space in the pores of these dishes. This is what we call, let's say, the pore space. And then when you do the dishes, all these plates are much nicer aligned, so they fit in a much smaller volume. And this is the same process that happens in the subsurface in these clay layers. So simply these clay particles, which are also plate-like, they realign and rearrange, and they become much thinner, and that causes a lowering of your land surface. So what we did, and I'm going through this one a bit fast, so we tried to put this in a computer model. So we built a big 3D model with a lot of different data in there, and we had great help from Vietnamese colleagues who were able to get all this data together. And with this model, when we finally constructed it, we could try to simulate the effect of groundwater extraction on the hydrological system and also in terms of land subsidence. And we see here the effects of the extraction since 1990 going into the 2015 in this simulation. And on the left side, we see the drop in hydraulic head in one of the aquifers. So you can say, let's say, water level in the aquifers. And on the right side, we see cumulative compaction. So this is the entire cumulative response of all the model layers in this model. So we especially see in this part where we see the earliest drop near Ho Chi Minh City response. And then later on, after 2000, when we really see extraction increasing in the delta itself, we also see a response in the delta. So we actually simulated this accelerating trend of land subsidence, going from the 90s, when there was hardly any extraction, into the 2000s. And it is much higher than the global sea level rates. When we did this simulation, we only had this INSAR data set to validate what we did with the model. So as you liked it, this was sitting right here in this sequence. And then later on, last year, we actually got a new data set. And it shows that in 10 years of time, there is indeed seemingly an acceleration taking place in land subsidence. So this confirmed also the trend that we saw in the model. So groundwater extraction is actually affecting almost the entire delta at this stage. So let's go to a global perspective. So this is not just happening in the Mekong Delta, of course. But if we look to a lot of different delta systems around the globe, we see similar kinds of responses and rates. Well, for example, here, this is up to 3 centimeters a year in New Orleans. Myanmar, Irrawaddy Delta, there's rates up to also several centimeters a year. Some high rates up here in China and here in Indonesia. I hope this is not bothering you too much, the sound. Let me know, Paul, if it's a problem. So what we actually see here is that humans are sinking deltas much faster than the sea level itself is rising. So what is happening? What are the impacts of land subsidence? Now, first of all, there's damage to infrastructure. This is the most, let's say, visible one, and it can be very annoying to people who have actually problems with it. For example, you can have, if you have differential land subsidence in the shallow part, you can have foundations starting to crack. So all the pipes leading from your house and the street, they break. You can see that bridges, or for example, here in the city of Venice, when you walk around, you see multiple of these towers standing tilted like like the Tower of Pisa. But for example, also in Amsterdam, the capital of the country I'm from, this is one of the typical views when you exit Central Station. And if you put a horizontal line here, you see all these houses. They are quite tilted and moving because of shallow compaction in this case. If your land level is lowered, you are more susceptible to flooding. An example here is from Jakarta. Jakarta experienced a lot of land subsidence due to the extraction of groundwater, with some areas up to even 4 meters. And that's why it's now really, and it's actually still experiencing very high rates as we speak. And this makes it very, let's say, susceptible for flooding. And if you follow the news, there has been, for example, these major floods at the start of this year. And it's been quite an, let's say, hard situation, hard to control. And it's part of the reason why also, for example, the government decided to, let's say, move the capital from this place. However, I don't think they will move all the people. So you still have, let's say, big issues towards the future. And then there's another issue is the increased salinization. So water becomes salter, and it's acting both in the subsurface, but also at the surface. So we have flooding events with salt water. And because if you have, for example, deep-rooted land subsidence, you also lower the base of your channel system. So this means that salt water can intrude much further into the channel systems of a delta, and thereby bringing salt water into the system as well. And well, we see here, these are different, let's say, models of salinity for different places, different deltas around the world. And it really shows that the amount of fresh water in the subsurface is really decreasing in many of these deltas. And that can be very dramatic in sense for our ability to produce food in these deltas. Another thing which can happen is the respiration of soil. So land subsidence is often coinciding with the emission of CO2 if there's, for example, organic matter being oxidized. And we see that here, for example, in a peat dome, when there's drainage and the groundwater level is lowered, it means that part of this peat will start to oxidize and release CO2. And this is also actually the main reason that the Netherlands is below sea level for a large part in these days. So we started as, let's say, a bowland, which was above sea level. And then when we drained this in the past, let's say 1,000 years, we very effectively, let's say, oxidized many of our peats. And we ended up in this situation where we are now, what we call Holland. So it's below sea level. Okay, and the ultimate threat of land subsidence, if we don't, we're not able to stop or manage it, is the permanent inundation. And this is, for example, what happened and still happens. This is a village outside of Manila, and in the past, 20 years ago, these were farmers, and they used this land to farm rice and other kinds of terrestrial products. And as you can see now, they are living in these permanently inundated circumstances. And this is due to the extraction of groundwater. And because of the extraction, actually it still continues, and the land is still losing quite a lot of elevation every year. So this is really, let's say, the end stage of if you fail to mitigate land subsidence in deltaic areas. So there's two strategies to do with land subsidence. The first one is to adapt. And that means, let's say, you deal with the consequences, so you cure the symptoms. And this can work if you have natural and unavoidable land subsidence. It can be engineering, building high levees. It can, for example, by reintroducing sedimentation, but also by non-technical measures, better spatial planning and governmental embedding, for example. The second one what you can do is mitigation. So this actually deals with the cause. So instead of fighting the symptoms, you try to cure the disease. And this works for, let's say, human-induced lens subsidence. What we cause ourselves, we can also try to not cause ourselves, right? For example, diminish the amount of groundwater pumping, aquifer storage, or using lighter materials for buildings. But in order to mitigate, it is very important that we know what is happening and what is causing land subsidence. So one example of adaptation can be to have a sedimentation strategy. So here we see some options of, let's say, constructing new ways, new flow ways of putting sediment into our delta systems. So actually building with nature and the existing materials that we have. It is important for this to understand the magnitude. And this is something what J.C. Witschke also mentioned in some talks back, this phrase. And I mean, it's important to know if there is, first of all, how much sediment do you have and is it enough to counterbalance land subsidence? And on the right here, this is let's say, back of the envelope calculation for the Mekong Delta. And here we see actually that the amount of suspended sediment in the rivers is by far not enough to counterbalance the present day extraction-induced land subsidence. So it is still very viable to look into this strategy, but it's not going to be able to counterbalance everything. And another thing is, what is important if you think about these sedimentation strategies is that when you increase sedimentation, you can also actually increase land subsidence. So you need to know this dynamic between sedimentation and increased compaction. And we are still getting better at being able to model and calculate this dynamic. For example, this is one of the reasons we now have this laboratory installed in the Venice Lagoon to characterize important parameters for these calculations. Because in extreme cases, for example, if you have very soft sediments, a sedimentation strategy could in the end even lead to a loss in elevation instead of a gain of elevation. These are, for example, some calculations done for the Mississippi by some colleagues. If you have very heavy sediment, for example, sand, and you put it on very soft sediments, maybe the weight of this sand is creating more compaction than the actual elevation gain you get through the new layer of sand. So this is really something to take into account when you start designing these kind of strategies. And other option is to go for mitigation. So in order to do so, we want to know what is happening in the future. So a way to do this is to, for example, develop a pathway approach. And we designed something like this for the Mekong Delta, different extraction pathways in what kind of how much groundwater extraction we can have in the future. So we have non-mitigation strategies in which groundwater extraction continues to increase towards the end of the century, and mitigation strategies in which we, let's say, the amount of groundwater extraction stabilizes or even decreases. Well, putting this in a model enabled us to create different outlooks into the future. So what is an interesting thing to see, so here we see the different scenarios and different land subsidence rates. If you look at the M4 scenario, which is the one down here, it actually is a complete stop of all the extractions since 2018. So this is unrealistic, but to see how the system reacts. We still see quite some land subsidence happening, and this is because the system is out of equilibrium. So that means even if you stop the forcing of the change, still the delta will continue to compact because there's still, let's say, ongoing compaction in these clay layers, which are not yet in equilibrium to the rest of the system. So this is very important, that it's not a process that you can stop from one day to another. If you set it into motion, it is actually going to continue. Well, through this approach, using these kind of models, we can actually design these kind of images that we see on the right now. And it helps us in a way that we can now, let's say, view land subsidence in a similar way as we view sea level rise. And this makes it also able to, let's say, compare the impact of the two motions of the land going down and the sea going up. So what we actually see is that the decisions that we take today, they actually determine what will happen in the future to these deltas. And we try to quantify the impact of these different scenarios in terms of land subsidence and combine it with global sea level rise and the elevation of the delta. So if we go for a mitigation scenario in which we really reduce the amount of groundwater extraction, and we then look to the, let's say, relative sea level rise as if that is determining the exact elevation in the future, we see that this is the future trajectory of elevation for the Mekong Delta. As soon as you see blue arriving, it means that the elevation falls below mean sea level. If we go for the mitigation scenario in which we keep the amount of groundwater stable, we see this. So we see more blue, and at the end of the century, let's say half of the delta is at or below sea level. And if we continue to increase groundwater extraction, we see a worsening of this situation right here. So the key message is that actually freshwater extraction is not a free resource, because you pay in terms of elevation and in terms of salinization of your groundwater. Okay, so for this assessment, we actually assumed that natural compaction is compensated by sedimentation. So we didn't include any of these terms through this assumption. If we go to an assumption where we say, okay, there's no more sediment reaching the delta, so we do include natural compaction, actually the projections, they will look like this. So we see much, especially along the coastline, we see areas disappearing much faster below the blue, because these high natural compaction rates are located in those areas. So it is obvious that this delta really also needs the sediment in these coastal places. So if we want to go towards solutions, it is very important to create the awareness of the fact that humans are driving environmental impacts and are driving land subsidence. And it's not just, let's say, sea level rise and climate change, but it's rather human-induced effects that we see in these deltas. It is important to also understand the connection of the natural system, so we can design, let's say, working strategies of mitigation and adaptation. And these pathways, they're very useful tools to do so. So specifically, shortly for Vietnam, what are, for example, recommendations? It's the reduction of the extraction of groundwater, searching alternative water resources, switching to surface water or stored water, going towards more water-saving practices and smart agricultural use, and trying to, let's say, store excess fresh water at the surface or in the subsurface when you have it available. And it is also very important that there's no one solution that fits all. So it is actually, if you want to solve it, you have to have, let's say, multiple solutions that that fit into each other as a puzzle. And for that, you need to understand, let's say, the entire system. Also from, in this community, from a source to sink perspective. So to give you a summary of the processes and drivers of land subsidence. So land subsidence, it can be very highly variable in time and space. So we talk about this 4-dimensional problem. There's a strong link with human activity and also the use of subsurface resources. We see that human-induced rates, they tend to be much higher than natural rates in these deltas. The only exception may be if you have these very fast prograding deltas in the past, then you can have these high natural compaction rates as well. And it's also the case that, let's say, the dominant drivers and processes, they really vary from delta to delta, but also within a single delta. So if we have this diagram below here, let's say, every location you are in a delta, anywhere in the world, the situation will look, let's say, a lot different or slightly different. So this is really always the challenge of when you're studying land subsidence, trying to actually fill in all these components. Some take-home messages. So we see human-induced rates are much higher sinking our deltas than global sea level rises. It's no longer able to only go for adaptation strategies. So it's really important also to go towards the root causes and try to mitigate the practices that we as humans are doing to that creates land subsidence. These pathways, they are really useful in combination with scenario modeling, and they also give us tools to bridge the gap between the natural system and the socio-economic system. And this is really important that these two are being brought together. Another thing is what it creates an action perspective, because you can really show, let's say, the effect of certain measures or not taking certain measures on the future evolution of a delta. Then the inclusive delta system approach, it echoes a bit the point before, and this is, let's say, it's a call to arms for everyone, let's say, to work together and not sit in its individual discipline, because only if these different disciplines are talking together and also across natural and social boundaries, that's the only way to come to really effective management strategies of our deltas. Then I'd like to show you just this slide with some additional resources if you want to read up some more on these topics. So, for example, there's the UNESCO Land Subsidence Initiative. You can find it here. There's increasingly amount of resources on land subsidence and the causes of land subsidence and what you can do about it. The Delta Alliance, it's a group of deltas worldwide that are connected, and they have also quite nice resources. So recently there's, for example, a new policy brief on how to deal with land subsidence and what kind of action perspectives you can actually do when you are trying to manage a delta that experiences this. There will be on the 4th of December a workshop at Utrecht University, and it's on sedimentation strategies in deltas. So it can be interesting to join if this is something that you're doing. And then in the current project at Padua University, we are, let's say, continuously developing, let's say, the way that we can predict accurate land subsidence for deltas into the future. So you can stay tuned, follow us on Twitter or on the website that will come up in the near future. Okay, with that, I'd like to thank you for your attention. Thanks.
Philip, thank you very much. Such a fantastic talk. Give us such a good overview about the delta subsidence, particularly about the Mekong River Delta. We now have a much better understanding what's going on and possible future. So before I go to the specific question, I want to make a little bit comments and also a short question. You know, as you mentioned, the subsidence now become such a severe problem in the coastal city and coastal delta area. And for example, in Asia, all the way from Tokyo, Shanghai, Manila, Jakarta, Bangkok, Saigon, you know, maybe Dhaka also. So last 2 years ago, our friend Yoshi Saito took me to the suburban of Tokyo. It's unbelievable. It's a 4 to 5, some place go to 6 or 7 meters already. You know, the ground sink, and many living community even much lower than the surrounding river. So I think Jakarta maybe still have some space to go down. It's not the worst yet. Jakarta only 2 or 3 meters someplace. So it could be go to 5 or 6. So my question is, based on your understanding, is any example, any case, any city have a good mitigation, a good example to stop or prevent that kind of subsiding. I know Shanghai did a pretty good job. It's much slow down the subsidence. Bangkok maybe slow down a little bit, but how? I mean, New Orleans still, I mean, thinking, and other place. So, what's your? Do you have quick comments?
Yeah. So actually, the first example you gave. So Tokyo had a history of land subsidence in the 1960s, and they indeed lost several meters, up to, let's say, 4 meters, maybe some areas even more. But they effectively managed to stop this process because of they basically banned the extraction of groundwater. And what even we see, if we look at the measurement records, is that Tokyo, after going down for 4 meters, it rebounded again several decimeters because groundwater was recharging. So actually, Tokyo that's one of the examples where, let's say, already mitigation was successful. And another one is, for example, the city center of Bangkok is also successfully, let's say, land subsidence has ceased because of strong measures to reduce groundwater extraction. Yeah.
Wonderful. Maybe one day I think we can maybe bring a colleague from Japan or maybe even Thailand to talk about their successful story. You know, a quarter successful. You know,
we should. Yes, we should. They have experience.
Okay, we have a couple questions from our audience. So Hong Quan, our Vietnam colleague, Hong, could you unmute yourself? Ask the question directly. Hong Quan, are you able to unmute yourself? I didn't see. Oh. No, okay. Go ahead, ask the question. Hong Quan.
Okay, thank you, Paul. Thank you very much, Philip, for a great talk. Yeah, I saw a lot of progress in your last presentation you have here in Vietnam, Philip, especially in the last slide, I think around 18, when you have updated simulation result. Yeah. So, do you have any separations of the impact of different factors on land subsidence in the Mekong deltas?
Thanks, Quan. Yes, but we actually have current work is really to try to split it apart, and we have more and more, let's say, detailed ideas of being able to split these factors. But it's not something I put in this talk, also because it's quite, let's say, specific. So we can, for example, much better unravel now if we look very closely to INSAR data and we combine it, for example, to models and to subsurface information. We are able to, if you remember this diagram, go from, let's say, total land subsidence, as you want, as measured by INSAR, and try to distinguish it in the depth and then link it to different processes. So we are able to do this kind of exercise. We actually just, let's say, arrived at that stage for the Mekong Delta to be able to do this. But it does require, let's say, all this preparation of these different models, different measurements, different understanding the subsurface in order to arrive at this stage. So it is quite exciting, let's say, to see what we can do in this in the near future.
Yeah, thanks, Philip. Thanks, Paul.
Jim.
Thanks, thanks, Paul. Thanks, Philip, for a wonderful talk. It's just a whole fascinating range of things you went through. I was going to ask you for your case example with the Mekong, when you looked at future extraction strategies and substance predictions, given sort of likely population growth and land use change and urban growth, what's the most likely projection scenario that you see given those current predictions?
So let's say when we started this development, first the model was built until let's say 2015, and this was also what we have in terms of monitoring of the groundwater levels. If we now compare it to recent measurements of groundwater level, we see that the delta is on the trajectory of actually the sustained increase of the extraction of groundwater. There's so far all the measurements don't show any let's say delay of or let's say delay of overexploitation. So there's still a drop of hydraulic head. So in that sense, if we go back to the trajectories, it means that it is currently around this B1 trajectory, still going to 2020. There is a lot of, let's say, current developments in Vietnam going on, and a lot of initiatives to really try to reduce groundwater extraction. So it's going to be, let's say, very interesting in the next years what is going to happen. And I hope, of course, that they will manage to, let's say, bend this line and go into one of the more favorable predictions. Yeah.
But does that current curve, does that include predictions for changes in population or urban growth that could change the groundwater extraction rate?
So in this case, we haven't connected it one-on-one to these projections, and that would be the next step. So this is more from, let's say, the first step in which we just threw these crude assessments into the model. The next step would be indeed to link it to these accurate, maybe let's say, social development pathways, but also to make it, let's say, locally, spatially varying, and you can also. We already see different responses for different areas in these delta. So yeah, we actually should try to capture that as well.
Okay. Thanks very much.
Eugene, go ahead.
Oh, you want to put in me? Okay. Well, thank you for a wonderful talk. I learned a lot. As you said, there are multiple reasons that could lead to land subsidized groundwater use, sediment. My question actually goes to the other way. Do you think was land subsidence actually trap more sediment? If the river supply of sediment is similar, would it trap more sediment, or allow less sediment supply to offshore, or it's the other way around?
This is an interesting point. So let's say if you have lowering of your land, you create accommodation. So in that sense, if land subsidence allows more sediment to be trapped on the terrestrial part of the delta through floodings and those kind of mechanisms. Even though, I think one of the other talks in this lecture also talked about when these channels are sinking and let's say that the land part is going down, it means that also there's more tidal ingression, and it also traps more sediment coming actually from the sea into the tidal systems instead of being then supplied to the coastline. So I think for sure, let's say in a natural situation, if you have more land subsidence, you have much more trapping capacity for sediments.
Thank you.
Good.
Thank you.
Bill, go ahead.
In coastal Virginia, U.S., we're seeing ground subsidence due to, we're taking out about 130 million gallons a day from the Potomac aquifer, which is a closed aquifer. That's about the same, that subsidence equals the amount of sea level rise we're seeing. What we're trying to do is we're trying to pump reprocessed wastewater to reverse this subsidence. I wondered if this was something that's being tried elsewhere and if this would be feasible on a delta. Thank you. Let's say
to answer the first one, to try elsewhere, I think, let's say, managed aquifer recharge or recharging aquifers, it's quite common. It's done on a broad scale, let's say. For example, in Shanghai, they're doing this, and many other places, at least, they're piloting this kind of things. The issue is, I mean, if you say they extract groundwater, but I mean, they do clean the wastewater first, right? So in this case, right. And I think that's a very important step, which is hampering, let's say, as we speak, the the widespread implementation, because let's say the availability of a lot of this fresh water, well, in case of this delta, then the water quality is not high enough to be pumped in directly, so you have to treat it. But if you have to treat it, if you then compare the amount of water that's being extracted, it is almost, let's say, an impossible task to put the same amount of water back into the subsurface. And even if you do so, then it's maybe even you could even make a closed surface system, so you don't have to rely on your groundwater system if you have that amount of surface water available anyways to pump down. So it's not a matter of, let's say, technique, I would say, but a matter of simply volumes and also the availability of good quality fresh water.
Thank you.
Thank you.
Michael.
Yeah, so I wanted to follow up on Jim Best's question, because he asked about the future, and one of the problems in the Mekong is that there's a large number of dams being built or planned upstream. And so have you taken into account the fact that the sediment supply is very likely greatly decreasing?
Yeah, exactly. So the amount of sediments is indeed going down a lot, and the most recent assessment is that there's only 1/5 left of original pristine sediment load. But then, so in these assessments, we assumed, because we didn't go into the amount of sedimentation that much, but we assumed that it counterbalances the natural compaction. So that's why we see on this right image. You can still see my screen, I think, right?
Yes.
So then here on the right side is if we exclude sedimentation, so we have this natural compaction adding in, so we see a much different, let's say, much more, let's say, a bigger loss in elevation. And I think I go a bit back to the sedimentation strategy now. So here, if we look to the amount of sediment that is in the pristine situation present in the river, it was about 160 megatons. That's let's say the highest estimate. And if we then calculate the present day sediment that you would need to counterbalance only extraction-induced land subsidence, yeah, we arrive at this rate. So it's completely not, let's say, it's almost an order of magnitude apart, because right now we are looking more towards this 50 or even less than the pristine load. Yeah.
Yeah, the full dam build out would actually decrease it by like 96%. So it's, it could be much worse. And you in your subsidence estimates, you mentioned buildings and infrastructure. How large is the loading effect of buildings and infrastructure? Yes, that's something I haven't looked into.
You mean how large the effect is?
Yeah, because you showed that as one of the human-induced causes of subsidence, but I've never seen any estimate of the magnitude of subsidence that buildings produce, buildings and other infrastructure.
Yeah, exactly. So, well, the infrastructure it's mainly it's a very local effect, right? So it's the infrastructure itself that is suffering this sinking, but it's not causing, let's say, infrastructure alone is not causing, let's say, a delta to lose elevation on a delta scale. To give you, let's say, an order of an idea, I once heard some colleagues talk about calculations that let's say the weight of an entire city equals the weight of 4 meters of groundwater level. So if you would decrease groundwater level in an aquifer system, and of course this completely depends also on local geology. This was let's say a case that was calculated. Then you would arrive at the same impact. So that gives you a bit of a, let's say, feeling of how heavy is a city in that sense. And if we look to the amount of groundwater level drops in this system, they go down towards 5, 10, in some places even 15 meters. So, well, you have multiple, let's say, cities in terms of weight compacting this sequence.
In Dhaka, the groundwater extraction has lowered the water table by over 70 meters already. So
70.
70, yes.
Well,
Okay.
It's quite a large effect compared to the way the cities. Yeah, because certainly you see, locally buildings will get initial compaction and settling over the first mostly decade, and then it levels off.
Exactly. Yeah, and it's mostly also a shallow signal because let's say the most top part is the most soft. So these buildings are let's say sinking in the top soft part. But let's say if you talk about land subsidence on a delta scale, the infrastructure is not your big contributor, of course. It's the other processes on large areas that cause it.
Okay.
Yeah, because right now I'm trying to separate out that shallow versus deeper subsidence and how it varies with depth. So that's a critical issue.
Okay. A quick question, Michael. How about the city of Dhaka? Dhaka also have a subsidence issues?
On our GPS, we're seeing, I'd say, 10 to 12 millimeters a year.
Wow. Still.
And it may be, we're not sure, slightly decreasing because they're beginning to, basically the aquifers under the city are going dry, some of them. And so they're moving the pumping farther out. And now there's plans to bring water from the Padma River and process it.
Okay.
Because they know they can't keep pumping from directly under the city.
Okay, cool. So
it's not even that much actually. If you talk about, let's say, 70 meters of drop and you only have this kind of 12 millimeters or something.
Well, per year.
Yeah. Yes.
Yeah.
Yeah, one centimeter. Yeah. So I think it's already. Any other question? So Kwai, do you have a quick question or?
Yeah.
Quick.
Yeah,
Okay.
if it's loud, yeah, if it's loud, yeah. Just
yeah, you are the last question.
Yeah, thank you, Paul. Yeah, Philip, you just you mentioned about the impact of the sedimentations on the land subsidence. So, is there any evidence on this critical these issues over the globe about this one? Because actually, we are thinking about trapping sediment as a solution for land subsidence mitigation. But now I think it's the first time I know you said that the sedimentation also increase the subsidence. So it's really interesting point. So can you elaborate a bit further on this? Thanks, Philip. Thank Paul.
Yes. So let's say in principle, it is always good to let's say reinstate sedimentation in that dark areas. That's a natural process that's been happening, and that's actually been keeping and building elevation for the past millennia. Let's say my specific comment here, it's a bit of a definition question, right? So yes, you increase land subsidence, but if you add enough sediment, you can still have elevation gain, right? So that's the difference between land subsidence and the surface elevation change. In principle, most of the sediment you will add will result in a net elevation gain. So it's a good thing. The example, let's say the extreme case that I'm mentioning here is if you have, for example, a very weak peatland area, and you build really a diversion of your entire river, creating, let's say, a crevasse play. Then you also introduce much more heavier materials, let's say sand and maybe even gravels, and they are much heavier than the peat that they deposited on. And you could actually, in specific cases, arrive in a situation that the weight is so much, and you create so much compaction of the softer fine-grained deposits below, that eventually you lose the almost equal amount of elevation gain of the new sediments. But so it depends on the material. But if you talk about, let's say, sedimentation, and you talk about suspended sediment, so by reintroducing floodwater into your floodplains, that will not be, let's say, it will not create a net elevation loss. No, I don't think so.
I find it hard to imagine the compaction exceeding the thickness of sediments you add. I mean, it could certainly take up a substantial amount. I mean, easily 50%, and maybe in some cases, you know, a much higher percentage. But I find it hard to believe that you actually end up with a net elevation loss. It just may be that if you're just calculating that elevation, the sedimentation gain, your elevation rate is much lower than what you think it is.
Yeah, exactly. That's for sure something to account for. And let's say from the experimental calculations, there was some of the calculations ended up eventually in a negative elevation gain. But I think it's I'm not sure how realistic these are.
Yeah.
But,
some of that may be sort of the backlog compaction that was still ongoing.
For sure, yeah, for sure.
Because
that is the case.
Not induced.
Okay, I think now, you know, we have to end it here. Philip, this is a fantastic, as you can see, the response. But to be honest, we have to realize the subsidence naturally is not a bad thing. It's a normal process, normal natural process. But because human being, we put because it's against our interest, you know. So it's sometimes we have to pay a price, you know, to against the natural process. That's, you know, that's the human history, always fight the nature. I don't know we can succeed or not, but you know, this is the way human history. So, but anyway, so this coming Friday, Bob Ella will talk about the carbon process. So thank you very much, Philip, for this wonderful talk. Philip, could